All right, we're going to start our first chapter of Chem 122, which is actually chapter 13, because if you remember, we did 1 through 12 already. So we're going to talk about properties of solutions, okay? And remember, solution is a homogeneous mixture, which means it's a well-mixed mixture, okay? Two or more pure substances, you mix them together, you mix them up well, but they're not chemically combined, okay? In a solution, you have the solute. That's what disappears or dispersed uniformly throughout the solvent. So like if I made a salt water solution, salt would be the solute, water would be the solvent. And water is the most common solvent. So the thing that kind of disappears, I guess, if you want to call it that, would be the solute. And then the solvent is what does the dissolving. Okay. The ability of substances to form solution depends on several things. Okay. One of it is, do they like to mix? Okay. Do they have a natural tendency toward mixing? One is the intermolecular forces. We talked about those before. That's like the dipoles and the London dispersion forces. So the forces in between the molecules. For instance, the reason why salt and water can mix is water is a polar substance with positive and negative ends, and salt is an ionic substance that has positive and negative ions. So they mix up well because the polar part of the water can mix with that. If you take a nonpolar and a polar, that's probably not going to happen. Okay, so when you're talking about natural tendency toward mixing, mixing of gases is by far the most spontaneous. They'll just mix right in together. Okay, here's an example of oxygen gas and argon. And one thing, again, is each thing is going to act as an individual substance. They're really going to move independently of each other. Okay, so each gas acts if they're in a container alone, and they're going to fill it up. The mixing causes more randomness in the position of the molecules, and what they do is they call that an increase in what they call entropy, okay? Increasing the thermodynamic quantity, all right? That's called entropy. We'll talk more about that later. We've already talked about enthalpy. Enthalpy is the increase or the decrease in heat, but entropy is the randomness, okay? So when you mix gases, they like to increase in their randomness. Okay, so the formation of solutions is favored by an increase in entropy, an increase in randomness. Okay, that's what happens when you mix things together. Okay, so when I already talked about intermolecular forces. Okay, here's dipoles. We talked about those where they're a polar substance and they have a positive and negative end. There's also hydrogen bond. Hydrogen bond is the strongest of all these bonds. Okay. The ion to dipole, like I said, sodium, and here's sodium and water. Sodium is positive, and then you have your chlorines, which are negative. What will happen is the positive end of water, which is the oxygen, will be attracted to the sodium, and then the negative end, sorry. This is the negative end, this is the positive end. So they're going to situate themselves so that the negative is attracted to the positive, and the positive of the water is away from the positive of the salt. So your chlorine are going to be over here if you're doing a salt solution. Okay, so the intermolecular forces of attraction, anytime you have a force of attraction between the solute and the solvent, in this case water would be the solvent and salt would be the solute. Here's another example. Ethanol is mixed with water. Solute, solvent. Okay, so anytime you're mixing things together, you can have these forces: the dispersion forces, the dipole, the hydrogen bond, or the ion dipole. They can cause the mixing of the substances. Okay, so attractions involved when forming a solution. First, you have the solute to solute interactions in the solute itself. Okay, you have to overcome them if you're making a solution. In other words, you have to break those bonds in the solute itself in order to make a solution. Okay, that's why we dissolve the salt or any other solid in a liquid. Okay, you have the solvent-solvent attractions. Okay, you have to overcome the attraction, like for instance in water. You have to be able to insert something in between those water molecules to make room. So we have to break those bonds to get the solute in there. And then the solvent, the solute itself. Okay, we have to get those to interact. Okay, so when you're making a solution, and again, we're doing a physical thing. It's not a chemical reaction. It's just a physical thing. But you have the solute-solute interactions to overcome, the solvent-solvent, and then of course the solvent-solute. So you have three interactions to overcome in order to make a solution. Okay, salivation, not salvation, sorry. Salivation is hydration. okay? Adding water to things. Here's a crystal of sodium chloride salt, and you can see the little water particles get in there and they start to overcome those forces. Here they are individually. But really what they do is they just kind of, I don't know, they're like Pac-Man. They kind of grab the pieces and break them apart. But basically water surrounds. And again, here's going to be your positive hydrogen part. They're going to be attracted to the negative chlorine part. Here's your negative oxygen part. It's going to be attracted to the positive sodium part. So they're basically just going to break up that crystal, and that's why it dissolves. The water just kind of forces its way in and breaks it up. Okay, so this is an example again with where salt is the solute and water is the solvent, and that's how water can get in and dissolve these little crystals. Okay, whenever you're looking at a solution formation, we've talked about exothermic and endothermic. Okay, if making the solution causes an increase in heat energy, if it gets hotter, that means heat is being released into the environment. Okay, that's an exothermic. If it gets cooler, that means the system is absorbing energy, and it's going to be endothermic. And the way you can tell by temperature wise is it gets colder. Okay, so we've got that endo and exothermic coming up again. So for an endothermic reaction to occur, the delta H, we talked about that of the mixture, that's enthalpy, must be close to the sum of these two together. Excuse me. Okay, entropy again is randomness, and that will help with that. But when we're talking about when we have this is enthalpy, that's basically the change in heat. But they have to be close to each other in order for that to happen. Okay, exothermic reactions are spontaneous. For an endothermic reaction to occur, you have to do something. It doesn't just happen. You have to make it happen. You have to add energy to it. You have to do something, okay? But an exothermic solution will, these can happen without you doing much. You know, they don't need that extra boost, if you want to call it that, okay? Okay, anytime we say it's aqueous, that means it's dissolved in water. So an aqueous solution versus a chemical reaction. When we're talking about an aqueous solution, we're just dissolving something in water, okay? The substance, they're still the same, okay? It's a homogeneous mixture or a solution. It is not a chemical reaction, okay? Here is nickel and hydrochloric acid. The nickel actually just keeps its form. If you take, if we put them together, now if this is hydrochloric acid, let's say we add water to this would just be a mixture. We put nickel in there, we actually end up with a brand new substance. So we know this is a chemical reaction. Whereas if we add, like I said, if we add water to something and they keep their properties, okay? Like if we make a saltwater solution, we know the salt is still in there. If we just boil off the water, we'll have a salt back. So when you're talking about, if it looks like it's dissolved, but if there was no bubbling or fizzing, because remember that tells you there's a chemical reaction. If there's no, what were the other ones? Heat or light given off. There might be a slight change in temp, but not like, you know, when we did other reactions. Or a precipitate is formed. If none of those happen, then you know it's just a physical reaction. You're just creating a mixture, okay? Okay. Whenever you're making a solution, you can add solid particles to a point, and then at that point, you can't add anymore. In other words, it's dissolved all it can, okay? So you take your solute and your solvent, and they're going to go back and forth. They're going to dissolve, and they're going to recrystallize, and that's what this double arrow means. It's going back and forth. They're opposing processes, dissolving, recrystallizing. When they reach that point, they're at equilibrium. If you add more solute and it doesn't dissolve, okay, you've reached what they call saturation. And this isn't going to, you know, you're going to just get more crystallized. Actually, you're not going to even get any more to dissolve because they have a max that they can do, okay? So the rate of opposing processes is equal, okay? So when you get to the point where you've added particles and no more will dissolve, in other words, it's reached its max, what is happening there is these two guys are mixing together and they're dissolving and making a solution, but you'll also get some that recrystallize back. So you get some solute particle back. This is at equilibrium. If you add more solute, you're going to screw up the whole equilibrium and it's not going to dissolve anymore. So when the rate of opposing processes, dissolving and crystallizing, are equal, Okay, so if you add any more crystals, it won't dissolve. This is a saturated solution. It has taken all it can and you can't add any more to it. Okay, if you've not yet reached that a point where, in other words, you're adding solute and it's dissolving, you're adding solute and it's dissolving, when it keeps, you can keep adding it. When you get to the point where it doesn't dissolve anymore, that's saturation. But before you reach that point, that's unsaturated. Okay? Okay, so solubility is the maximum amount of solute that you can dissolve in a given temperature. Usually, if you increase the temperature of the solvent, you can dissolve more solute. Okay, that's a kind of a generalization. It's not true for everything. But solubility is the maximum amount. If I'm making a saltwater solution and I have like 100 milliliters of water, let's say I can add 4 grams of salt. That's its maximum saturation. If I add more than that, it doesn't dissolve. Up to 4 grams, if I've added 1, 2, 3, it's dissolved. That's an unsaturated solution. So if I add any more salt, it won't dissolve. I've reached saturation level. Okay? Saturation have the amount of solute that they can dissolve. You can add more if you want, but it's not going to dissolve. Okay? And unsaturated is up to that point. So I kind of went through that already. So like I said, if 5 grams of salt dissolves in 100 milliliters of water, when I add 1 gram, 2 gram, 3 gram, 4 gram, that's an unsaturated solution because it can still dissolve until I add 5. After 5, now I'm saturated. If I add 6, it doesn't dissolve. So I'm wasting it because it's not going to dissolve anymore. Okay. And then one thing, most of the time when we talk about solutions, people think it's a solid dissolved in a liquid. That is only one type. There are several. Okay. There's also another type of solution that's called a supersaturated. If you guys have ever made like crystal gardens where you add that, liquidy stuff, well, that's a supersaturated solution. In other words, at a high temperature, you got to add a lot more stuff to it than you were supposed to, but the high temperature dissolved it. As it cools, it forms bigger crystals. We used to do this with like pipe cleaners. You'd make them like into little snowflakes and all that, and you dip them in a supersaturated solution of borax. You can buy borax in the store. It's used for laundry. But you can dissolve more borax than normal by heating the water up. It dissolves a lot more. And then when you put the pipe cleaners in it, as they cool, you get really cool crystals. And again, if you've ever made a crystal garden, it's the same kind of thing. As it dries, it forms really big crystals, and you get this really cool garden-like things. Okay? Not everything will make a supersaturated solution. Okay? But it holds more than it normally would because you've increased the temperature. And then again, when it comes back down, when it cools off, it makes bigger crystals than normal too. Okay? So, oops, I'm sorry, you guys. The solutions are unstable because you heated them up. Again, as they cool down, actually, if you add a seed crystal, they even form faster. But it's not that common, you guys. You can't do it with everything. You can only do it with certain things. But it is really cool when it cools off because you get really big, cool crystals. Okay? Where are we at here? 13. Okay. Factors that affect solubility. In other words, the things that affect whether a solute will dissolve in a solvent. Well, first you have the interactions themselves. Okay. The solute-solvent interaction. You have pressure. If you're talking about a gaseous solute, if you increase the pressure, you can dissolve more solvent in it and solute in it. And temperature. Usually as you increase the temperature, you can get more to dissolve. Not always, but sometimes you can. Okay. So if we're talking about solute to solvent, one of the terms you'll always hear is likes dissolve likes. What they're talking about is their bonding type. Okay, if it's a nonpolar substance and you add a polar substance to it, chances are they won't dissolve. If you put 2 nonpolar together, yep. 2 polar together, yep. If you put a polar and ionic, because you have the positive and negatives, they will dissolve each other. But if you put a polar with a nonpolar, that's not going to happen. Example is water and oil. Oil is nonpolar, water's polar. When you mix them together, oil and water don't mix. That's what they're talking about when they talk about likes dissolve likes. Okay? The stronger their bond, the greater the solubility of the solute in a solvent. So again, if they have stronger bonds, like ionic bonds, then they're easier to make a solution. Okay? And gases have only one force in them. They have London's portion. So they're more soluble in water. Okay? And you know what? I'm going to have to quit here because we're going to run out of 15 minutes. And sometimes I cut off in the middle. Sorry about that. You guys will just have to forgive me. All right. So that's it for now.